Okay. All right. So last time we were in the middle of seeing how we add forces to the equations of motion. So I'll remind you from last time that we had the hello there. I had speaker for a while and I didn't like that. Okay, so we had the equations of motion for in the Newton-Euler framework, and so these were the conservation of momentum equations for the bodies of our system. Okay, so mu a is the angular momentum. Then I had external torques, which I called tau, and then I had these things which I called interconnection torques, iota. And so I had one such sort of conservation of angular momentum equation for each body. Okay, and similarly for the linear momentum. And I called the interconnection forces there rho a. Okay. And what I was trying to do was characterize what it meant to be an interconnection force or torque. Okay. So these ones were the interconnection forces and torques. And what I stated, and I won't rewrite it here, is the principle of virtual work. And the principle of virtual work says, so again, the way that I phrase these things, you know, I want to make it clear. If you go and read any other book about mechanics, or if you Google it, the principle of virtual work will not look like this, but it amounts to the same thing. And it is that interconnection forces and torques do no work on admissible motions of the system. Okay, and so admissible motion of the system here for me means motions following a curve gamma, and the curve gamma is in Q, which is a subset of Q free, because these equations nominally are happening in Q free. Right? We just have rigid bodies and they're moving around and they're moving in Q free, but of course they don't move in Q free, they move in Q. But the thing that makes them move in Q and not just all of Q free are exactly these interconnection forces and torques. And so then what I did was translated the principle of virtual work into a precise mathematical statement, which I boiled down to the Lagrange force for the interconnection forces and torques. Okay, and I had decided that I would call this thing capital I, because it's interconnection force. So the Lagrange force satisfies that I, the force at time t. Okay, so remember what this is. This is a cotangent vector at gamma of t to q. Okay, this thing, when you hit it with any tangent vector to a curve gamma satisfying the constraints, or satisfying the interconnection that I sit inside Q. Sorry, this is cotangent vector. And this is, sorry, let me be consistent about how I label these. Okay, like so. All right. So this should equal 0 for any curve gamma in Q. All right, that was how I translated the principle of virtual work into something mathematical. Okay, and as I said, this is like an orthogonality condition, because as I run gamma over all curves in Q, then gamma prime, as the curve gamma passes through a point, little q and big Q, gamma prime is simply going to take all possible values in the tangent space at that point. Okay, and so this is saying that the forces, so it's not an orthogonality condition. It's in the sense that this isn't an inner product I'm using here, but rather it's the pairing between a cotangent vector and a tangent vector. But it's like an orthogonality condition because it says that this is like orthogonal to the tangent space. Okay. So geometrically, this means that I of t, okay, it is in the set of all, so let me first write okay, so I'm going to say that this is the annihilator, and so then I'm going to tell you what the annihilator is. So this is the annihilator of the tangent space at gamma of t, q. Okay, so the annihilator is rather like the orthogonal complement, except you keep in mind here that it's not an inner product I'm talking about. It's cotangent vector acting on tangent vector. Okay, so that aside, the annihilator is, like I said, it's rather like the orthogonal complement. So this is the set of alphas in t star gamma of t q free that annihilate every curve, every tangent vector in the tangent space at gamma of t. Right? So this is kind of like the orthogonal complement. Of the tangent space. To Q in Q free. Okay. Okay, so that's how you should think about what these interconnection forces and torques are. There are forces that do no work on admissible motions. Okay. All right, good. When we look at these equations, so again, let me kind of harken back to how you did this in first year. Okay, so what you did in first year, so sorry if you didn't get that, but I'll be back down there in a second. Actually, yeah, sorry, I can keep the whole thing on. Okay, so these equations are just really the force and moment balance equations that you would have written in first year. And this, I don't know what you called it, is like the inertial force, right? And so what did you do when you had a system like this? You eliminated these interaction forces between bodies of the system or between the body and its environment. Okay, and so it's a very, very elementary example. Okay, so suppose I have a block that's just moving like so. Okay, and let's say the block is sliding and it has some friction. Okay, so the body's moving with let's say displacement x of t, and there's gravity here, which is and the acceleration due to gravity. I'm not going to write it as little g. I'm going to write it as a sub g, acceleration due to gravity. And so, when you kind of draw this body with all of its forces acting on it, well, it has its inertial force, which was mx double dot of t. Okay, so that, excuse me, is that, right? Okay, and let's say that this thing is acted upon by a force. Okay, and let me do something, slightly unnecessarily complicated. Let's suppose that this thing is acted on by a force like that. Okay. So as you kind of know, the only part of that force that's going to contribute to the motion is the horizontal component, right? And so, all right. And so this thing, as I said, there's going to be some friction force. So as the body moves in the positive direction, there's going to be some friction force, and I'm not going to specify what the nature of that is. So let me call this just F sub friction. Okay, so depending on the nature of the friction, that'll be something. If it's viscous friction, it'll be proportional to the velocity. There's all kinds of other friction, rolling friction, Coulomb friction. Okay, but let me not get into the details of it and just write that as friction force. All right. And that's going to be the only horizontal force. Okay. And then there's also going to be vertical forces. And so the vertical forces are, well, there's the inertial vertical force, which, as we know, is 0. Because we're constrained to move in the line, and that's exactly kind of my point here. Okay, and then in the vertical direction, I have the gravitational force, which is mass times the acceleration due to gravity. And then there's also going to be, the vertical component coming from this thing. Oh, sorry, I forgot to include the horizontal component in this diagram here. So that's going to be, the way I've drawn it, it's going to be F cos phi, where phi is that angle. Okay, and then pointing down, I'm going to have a force here, which is F sine phi. Okay, right. So this is just what you did in elementary mechanics. And so then what did you do? You balance the equations, right? So it's m x double dot is equal to F cos phi minus the force of friction, whatever that is. Okay, and my double dot is F sine phi plus MAG. Okay. All right. And I'm sorry, but I forgot the point I was trying to make here is there's also, right, a reaction force here, which I'll call capital R sub y. Okay, so this is, and the way I've drawn things, I apologize. If y is positive going up, which it should be, then first of all, I'm sorry, I'm getting my arrows all pointing in the wrong direction. That should be up if y is positive. So this should be negative, the way I've drawn things, and then plus r sub y. Sorry about that. Okay, so does that make sense now? Okay. Okay, so that's what you did in first year. Okay, so then the constraint here, so let's just say the nominal configuration space of this thing, the way I've drawn it, is R2, but I'm constraining it to move only in the horizontal direction. So there's a constraint that I move only in the x direction. So I'm constraining it to a line in R2. Okay, and that constraint is going to require that this be 0. Okay, so in other words, for admissible motions of the system, y of t is constant, and so y double dot of t is equal to 0. Okay, and so that admissible motion is rather like asking here for tangent vectors to be in the tangent space to q. All right, and then I do my force balance, and so I get in the x direction I get this. And then in the y direction, I get, this is equal to 0. And so the reaction force must be equal to the sum of these two things. And, it's just what the force pushing up from the ground, which is the reaction force or the interconnection force, has to balance the forces that are pushing down, because there's no inertial force in that direction because of the constraints. And so when why didn't I draw a reaction force here? Why don't I have an Rx here? Sorry, an Rx here. Okay, I don't have that because the constraint force, okay, Ry, has to be orthogonal to the motions allowed by the system. And if I had a constraint force pointing in the x direction, that would not be orthogonal to the allowable motions. Okay, and so this requirement that I of t be in the annihilator like so is exactly, in this elementary example, the reason why I don't have a reaction force here in the x direction. I only have one in the y direction, right? It's orthogonal to the motions that are allowed. Okay. All right. Okay, good. So now we kind of understand what I think what interconnection forces and torques are. Right, and so in this example, of course is very simple. Essentially in this example you discard the vertical component and you only work with the horizontal component. But what you really are doing, you're not really discarding the vertical component. You're just using the vertical component to find the reaction force. Okay. And so it's not like the reaction force isn't there, and it's not like the vertical equations of motion don't contribute anything. They allow you to solve for the reaction force. Okay, and the same thing happens here. Except it's just going to be more complicated, but it's still really just linear algebra. Okay, so the point is, when you write these equations down, and they're going to be kind of messy in general, they're just going to be linear equations in these. Okay, keeping in mind that these are required to satisfy that condition. Okay, so subject to that condition, you solve these linear equations, and if your system is put together properly, then that will have a unique solution. Just like down here, there's a unique solution for the reaction force. Okay, and so you eliminate the reaction forces. Okay, so in practice, one eliminates the reaction forces. Okay, and this can be done just using linear algebra. Okay, and that'll be a messy process in general. Okay. Okay, so that's Newton-Euler. Okay, and that's kind of a very high-level view of the things that you learn to do in your first-year physics course. Now let's see how that translates into the Euler-Lagrange equations. Okay, so we let F be the Lagrange force. Associated to the external forces and torques. Okay, so these are the ones above denoted by tau and F. Okay, so this was the thing we did last time. Okay, in a couple of examples, we saw how to convert taus and Fs into a single entity, which we call the Lagrange force for the interconnected system. All right. Okay. So now, thus far, we've only talked about forces, but we have an interconnected mechanical system, and of course, it therefore has a kinetic energy metric. Okay. And I'm going to define, associated with that, a certain thing. It's an algebraic thing, and we've worked with it kind of computationally before, but now I'm going to just do it a little bit more carefully. So recall that since G of Q, okay, so when I evaluate the kinetic energy metric at a point, Q, what is that? Well, I know it's an inner product, and the thing I care about most here is that it's a, algebraically, it's a bilinear mapping on the tangent space at Q. Okay. And so associated with every one of these, remember, and so this is a long time ago, so I maybe don't necessarily expect you to remember this, but we did talk about this at some length. Okay, so we have, so this is a bilinear mapping, and so we spent some time thinking about the ways in which bilinear mappings are not linear mappings. And so a bilinear mapping, it's not a linear mapping on the tangent space, but we saw that it was a linear mapping from the tangent space into the cotangent space, or more generally, a bilinear mapping on a vector space defines a linear mapping from the vector space into its dual. We talked about that, okay? So, and we gave that thing a name. So if the bilinear mapping was B, we called that B flat, okay? And so we're going to apply that in this particular case. Oops. Linear mapping. G of Q flat, okay? And this goes from the tangent space to the cotangent space. Okay, and the matrix representative of this mapping in coordinates is just the components of G. Okay, keeping in mind that G is symmetric. Okay, so let me not write out the full details because we talked about this in some detail when we talked about linear algebra. So what do I mean? What's going on here? So the coordinates, okay, give me a basis for every tangent space, okay, and it's, you know, this basis. Okay, it also gives me a basis for every cotangent space, and it's this basis. Okay, and so therefore I have the coordinates give me a basis here and a basis here, and so I can ask for what are the components of this linear map with those bases, and it's exactly just the components of the bilinear map assembled into a matrix. Okay, so the best place to, if you don't remember us talking about that, the best place to come to grips with that, because it's in a much more simple setting, just plain linear algebra, is to go back and look at our discussion of this for vector spaces. Okay, but my need to talk about this because I want to talk about the inverse of this thing. So because G of Q is symmetric and positive definite, it's an inner product. Okay, that means the positive definiteness, especially, implies that this thing is invertible. Okay, and its inverse you won't be surprised to learn is denoted by G sharp. Okay. All right, and the components of G sharp are, okay, so you know from your linear algebra that the components of an inverse are the inverse of the components, right? So I just take this matrix of components and I calculate its inverse like a matrix, okay? And that's going to be the matrix associated with this, the inverse of that linear map, okay? So it's, these are, okay, so what the notation you use for the inverse, and this is what we talked about before, because when we talked about the Euler-Lagrange equations, I introduced the inverse matrix of this matrix when I was deriving the Euler-Lagrange equations and we were arriving at the Christoffel symbols. And you'll remember that the formula for the Christoffel symbols, right? So gamma J K L, it's 1/2 G J M, right? And this is exactly the inverse components of the inverse matrix of that. Okay, so we've encountered this these inverse components before, is the point. And we just denote the inverse comes from the fact that notationally we're writing the indices here as subscripts, and here we're writing as superscripts. Okay, so this is just the inverse matrix of this thing. Okay. All right, so that's the messy thing that's typically the thing that makes your expressions for your Christoffel symbols look unbearable, is that you have to invert that matrix. Okay. All right, so that's just notation. So so the point is we have this thing G sharp, okay, which we've kind of talked about before. Okay, so now I can state the main result about how the equations of motion are represented with forces in the Euler-Lagrange setup. And I'll state that as theorem. Okay. So we're going to consider an interconnected mechanical system with m bodies and configuration manifold Q in Q free, kinetic energy metric, G, and external forces and torques, F1, Fm, and tau 1, tau m. Okay. All right. So these are the, Newton-Euler representations of forces and torques, just exactly like we talked about when we talked about forces and torques. Okay. So forces are applied at the center of mass with a resultant moment, et cetera, et cetera. Okay. Then we have three equivalent. Oh, so sorry. I need one more piece of data. Let F be the corresponding Lagrange force. Okay, so then I have a list of equivalent statements. Okay. The first is that the Newton-Euler equations are satisfied with these external forces and torques and with the corresponding interconnection forces and torques. Okay, so that's a big jumble of words that I have to write down, so I'll proceed to do that. Let me make it clear here. So the following is equivalent for a curve gamma in Q. Okay, and the first statement is that gamma satisfies the Newton-Euler equations with external forces and interconnection forces. Okay, so again, these are not specified. These are unknowns that you solve for. Okay, but they're there somehow. Okay, so that's the first condition, right? So just to be clear, so forgive me, just to be clear, that means this. Okay. All right, so then the next statement is about the Euler-Lagrange equations. Okay, so I'm going to write down the Euler-Lagrange equations for a particular Lagrangian Okay, and of course, that's going to be the kinetic energy Lagrangian. And then there's going to be a modification term, which comes from the fact that there are forces. Gamma satisfies the, what I will call the forced Euler-Lagrange equations. Okay, so let me write those out. So they're the normal Euler-Lagrange equations, and so I'll write them in the most compact but least understandable configuration, because I've talked about what that really means. Okay, so those are the Euler-Lagrange equations. And then there has to be a modification coming from the forces. And this shows up in the simplest possible way. Okay, so remember that F is at every point along the curve gamma, F at t is a cotangent vector at gamma of t. Okay, so F therefore will have some components, F1 up to Fn, and those just appear on the right-hand side of this equation. Okay, so those are the forced Euler-Lagrange equations. So you just throw in the forces here. So I'm going to clarify exactly what those Fj's are. Okay, so where? L, of course, is the kinetic energy Lagrangian. And where, okay, so I've said what F is. F is the Lagrangian force corresponding to the external force torques. Okay, that's what F is. So we know how to calculate F. We spent some time independently talking about that. And so we know that F is going to look like this. Just because it's a covector. Okay, so it's going to be some linear combination of the basis covectors corresponding to the coordinates that I'm working in. And so those Fj's that appear in the Euler-Lagrange, the forced Euler-Lagrange equations, those are just exactly the components of the Lagrange force when you write it in coordinates. All right. And then the third condition is that gamma satisfies the forced geodesic equations. Okay, and these equations, well, you have the geodesic equations, of course. Okay, and with no external forces, the physical equations of motion are just that equals 0. But now it's not going to be equal to 0. It's going to involve F somehow, and it's not just F though. Okay, and why is it not just F? Well, if you remember, we went from the Euler-Lagrange equations for the kinetic energy Lagrangian to this thing. Okay. And if you look back at that computation, at the very end, we had to take the expression we got and multiply it by the inverse matrix here. Okay, and so now in this version, with the force on the right-hand side, we're also going to now have to multiply that by the inverse matrix, and that means G sharp. Like that. Okay. All right, and it can't be F. And it can't be F for the very reason that we know that this is a tangent vector at every time. Okay, but we know that this is a cotangent vector at every time. So it has to be a tangent vector, and that's what G sharp does. G sharp converts it from a cotangent vector into a tangent vector. Okay. All right, so so this is these three equivalent statements. Are sort of one of the major conclusions in the course, is that you end up with these very nice geometric equations down here, which tell you how the physical motions of the system are determined by the geometry of the system, namely the Riemannian metric, the kinetic energy metric, its Levi-Civita connection, and the Lagrange force, which comes from the external forces from Newton and Euler. Okay. All right. So what I'm going to stop here because I have to carry on. I can't finish what I need to do in any reasonable amount of time. So what I'm going to do next time is, first we're going to write these equations down in a couple of simple examples, just kind of by hand. And then what I'm going to do is I'm going to go through the Mathematica that I posted on the on QPage for the gyro system, just to kind of see how, first of all, how you use Mathematica to do that. So that's just, sort of a quick introduction to sort of using symbolic software to do these things, but also to make a point. And that point is that the stuff that we've done in the course so far has two benefits. One is that, as opposed to that. Okay. And so there's all kinds of good stuff happening in this equation here, which is really, really hidden in that version of the equations. Okay. So that's one thing. There's the version of the equations of motion, which are the force geodesic equations, make accessible to us some tools that we don't have if we're just writing down F equals ma and like we did in first year physics. Okay, so that's one thing. And then the other thing that I think is beneficial from this approach is that it really emphasizes a very algorithmic point of view of writing down equations of motion. And that is that there's very, very few places in the writing down in practice of the equations of motion where human input is actually required. And there's really just three places. Forward kinematic maps, the little r's and big R's, okay, as you know very well, you have to do those. You have to write them down in coordinates for your system. Okay, so that requires you doing something. Inertia tensors, so you have to figure those out somehow. So in this course, we've always made them easy, but generally speaking, that's going to require some effort from you. Okay, and then the third thing is, what are these external forces and torques? Okay, but then once you have those three pieces of data, the rest of this is just the computer will do it. Okay, and that's kind of the point, is that it takes some of the kind of artistry out of mechanics and just turns it into just a grinding computation that a computer can do. Okay, so next time we'll do some calculations, simple ones by hand, and then an ugly, complicated one by software. Okay.